All right, 4-4, indeterminate forms and L'Hopital's rules. So in the past, when we were doing limits, we would say, hey, let's do direct substitution and -1 plus 1. Well, that puts 0 in the bottom. That's not good. -1 squared is 1 times 2 is 2, 2 minus 2. We had 0 over 0. So what we said is that, okay, this is not going to be a value. It's undefined. So let's factor this thing. So we started factoring the top, and so we could cancel the bottom so we wouldn't get 0 in the denominator. We had the difference of perfect squares in the top. We canceled the x plus 1s. We had the limit as x approaches -1 now of 2 times x minus 1, which we could plug in the -1. It gets -2 times 2 is -4. Or when we had this example here, we said, hey, this is the square root of x minus 1. I put 1 in for each one of those x's. We get 0 on the bottom. How do I get rid of the bottom? I got to cancel it with the top binomial. Remember we had talked about this is technically a difference of perfect squares because I could rewrite x as the square root of x, all that being squared. And then therefore that would factor to this difference of perfect squares. And the giveaway was seeing this binomial appear with the square root of x minus 1. So we can cancel those. We now have 1 over the square root of x plus 1. We substitute in the 1. We get 1 over 2. And there's my limit. Okay? Which is fine and dandy. But the big what if, we get something where we can't factor. You have a trig function with an algebraic function, and there's no way to simplify this thing. If I take 0, I get 0 in the denominator for this x squared. Cosine of 0 is 1. 1 minus 1 is 0. I have 0 over 0. But I don't know how to factor and cancel this thing. Well, that's where L'Hopital's rule comes in. L'Hopital's rule states the following. If you take the limit of the top function and the bottom function in any type of fractional function like our previous example, and you get 0 over 0, or you get infinity over infinity, and it doesn't matter if it's positives or negatives, you can then do the limit of f of x over g of x as your x approaches c, and that's going to be equal to the limit of the derivatives. Now be careful here, we're not talking the quotient rule. L'Hopital discovered you just take the derivative of the top, you take the derivative of the bottom, reevaluate it at c. If you come up with a scalar value, it's a constant, then that's your limit value. If you come up with another 0 over 0 or infinity over infinity, which is still indeterminate, then you reapply the derivative rule again of the top and the bottom, and you keep doing this until you can get to a constant value. All right? So if we look at example 1, the one that we're struggling with here, we know this is 0 over 0. We do L'Hopital's rule. So you see this arrow with this L apostrophe H. That's the notation for, hey, I'm doing L'Hopital's rule. You take the derivative of the top, you take the derivative of the bottom. Okay, I'll do the tough part, 2x on the bottom. On the top, the derivative of just cosine of x is negative sine of x. So that negative and this minus make this now a positive sine of x. Well, wait a minute. That's 0 on the bottom. Sine of 0 is 0. Still 0 over 0. That's another indeterminate form. Apply L'Hopital's rule again. So we take the derivative of the top. The derivative of sine of x is cosine of x. The derivative of the bottom is 2. Ooh, that's a good thing. There's no more x's here. Now when I plug in 0, well, 2 stays on the bottom. Cosine of 0 is 1. And we finally get to what we call a scalar or constant value. We found the limit. All right, let's try our next example. 0 on the bottom when I plug it in. E, well, 2 times 0 is 0. E to the 0 is 1. So that's going to be 0 over 0. L'Hopital that thing. All right, derivative of the top, derivative of the bottom. I'll take care of the hard part. The derivative of the bottom is 1. On the top, it's e to the 2x. The derivative of that is still itself, but don't forget, because that exponent has the function 2x in there, you got to take the derivative of that 2x, which is just 2. That's what's being multiplied out to the front. Okay, well, we substituted in 0 before, and we got a e to the 0 was a 1. So now that's going to be 2 times 1 over your 1, which we don't need to have, and that's going to be a value of 2. We found the limit. All right, example 1, part C. If I put in infinity for both of these, it's infinity over infinity. That's an indeterminate. So L'Hopital's rule comes into play. We take the derivative of the natural log of x, and we take the derivative of x. Again, I'll always take care of that real difficult one on the bottom. That's 1. But the derivative of the natural log of x is 1 over x. Well, we don't need the 1 on the bottom. We can take the limit as x approaches infinity of 1 over x. We plug it in. That's 1 over infinity. That's small over huge. That means it's 0. We're done. Okay, example D. All right. Ooh, tricks here with negatives. X is going to negative infinity. So we've got to keep track of these signs here now. So if I put negative infinity in for x squared, that's going to be negative squared. That's positive infinity. Negative infinity goes in for this x. That's negative negative. That's e to the infinity. So that's a positive infinity. I have an indeterminate form. All right, so L'Hopital's rule. We'll take the derivative of x squared on the top. That's 2x. We'll take the derivative on the bottom. That's e to the negative x. But, again, chain rule, you got to take the derivative of the negative x, multiply that to the outside. That just makes it a negative. Okay, so we put the negative infinity in for x. So that's going to be negative infinity on the top. Negative infinity for x here, that's negative times a negative, that's positive, but that's just going to be negative e to the infinity. So that's negative infinity over negative infinity. I hate to say it, L'Hopital's rule again. So the derivative of 2x is going to be 2. The derivative of negative e to the negative x, well, that's actually going to take us right back to the original e to the negative x, because when you take the derivative of e to the negative x, it's e to the negative x, but taking the derivative of the inside exponent, that's a negative, multiplied to the front, so that's just going to change it to a positive. All right, we already put negative infinity in for negative x back here. That was infinity on the bottom. So 2 over infinity, that's huge on the bottom, small on the top, that's a 0. And we're done. You're going to love L'Hopital's rule. It saves a lot of time with difficult problems. All right, in this example here, we're going to try to find the limit as x approaches 0 of tangent of x minus x over x cubed. Okay. This problem, make sure you have lots of space, so write smaller maybe on your note sheets. All right, be sparing with your space. So I put 0 in for x. 0 here, and the tangent of 0 is 0. So we have 0 over 0. We're going to L'Hopital's rule. Oh, I can see why we need lots of space. We're going to have to do L'Hopital's rule, take derivatives of this x cubed until we can get that all the way down to a constant. So there's going to be a lot of derivatives going on here. So on the bottom, that's going to be 3x squared. The derivative of tangent of x is secant squared x, and the derivative of x is 1, so minus 1. So what I'm going to do here is I'm just going to factor out this 3. We're going to move that out front to the limit. Okay, we could, let's see. Oh, I do it later on. Okay, so substitute in 0, another 0. Secant of 0 is 0. Being squared is, is 1. Being squared is 1. So that gives us 0 on the top. So you might need to graph your secant function so you can find some of these values here. Or you can just think of secant as 1 over cosine. And cosine of 0 is 1, so 1 over 1 is 1, squared is still 1. L'Hopital's rule, this is going to be crazy here on the top, so be careful. So we technically have a chain rule on the top. Again, the difficult part, derivative of 3x squared is 6x, that's done. But let's talk about this top part here. The derivative of minus 1 is 0, so that's gone. So you got to remember that this is a chain rule. You have basically a big old x squared here, which would be 2 times x, but your secant function is playing the role of x. So this is 2 times secant of x. That's your inner function, is secant. Then chain rule says you got to take the derivative of secant, which is secant times tangent. So I really would have 2 secant x times secant x tangent x, and that's where I came up with secant squared x. So if you get lost on this one, ask this one. We have our open conversations during class time, and I'll write it up somewhere so you can see it. Okay, so now I factored out that 1/3 that I was talking about. And we're going to multiply that to the limit of secant squared x times the limit of tangent of x over x. So I separated that because I saw earlier back here that this secant squared of x was a 1. So now this becomes 1 times 1/3 times my limit. So basically cancels out. But again, I still have 0 in the denominator, and the tangent of 0, as we saw before, was 0. So we're still L'Hopital's the situation again. So 1/3 times the limit, again, tangent of x, that is going to be secant squared of x again, but the derivative of x is just 1. Well, this is a good thing. Remember, we've already done the limit as x approaches 0 for secant squared of x back here. That's a 1. So this is going to be a 1, and times 1/3, my answer is 1/3. All right, the limit as x approaches pi from the left. Be careful here. Now, you got to be, when you go right and left, you got to slow down. Do not make a direct substitution with pi and think this is 0 over 0. That's not true. What I did is I went to my graphs. Here's my sine curve in blue. Here's my cosine in red. So as I approach pi from the left of the sine function, that's going to be really small and approaching 0. On my cosine, as I approach pi, I'm really approaching -1. All right, so 1 minus a -1, that's going to actually be a +2, so 0 over 2 is 0. That's my limit. I don't need to do L'Hopital's rule here. They're trying to fool us. All right, so what I'm going to do here is I'm going to cut this in parts, and I'll catch up to you in the second part.